Salutations, fellow hunters of knowledge. Just checking that real quick. Welcome to the Universe Sandbox 2. I'm your host, Jacob Brown. That works. Now today I am here to show off Kepler's laws. In case you haven't heard of this game, it is basically a universal sandbox where you can screw around in space, and it's all fairly accurate. It does change a bit if you were to up the speed, trying to see what would happen to our solar system in a few million years. Currently it's traveling at a day per second. So, every 6-ish minutes, the Earth should have traveled one way around. Wait, no, yes, 6 minutes. Of course, it's traveling faster than that, so I would not bet on it. Whatever. Wait, 14.5 days not 1 day per second. I am a fool! It says it down here, 14 days per second, not 1. Whoopsie. Anyways, first order of business, Kepler's first law. All planetary orbits are ellipses with the sun as one focus, or at least planetary orbits in our solar system. So we shall check this. Mercury is traveling in, it's pretty close to a perfect circle, but there is still a bit of difference. It's not a perfect circle. Definitely not a perfect circle. Anyways, you can see that it is not centered around the sun, and based on its shape, I would assume its second focus to be around here. So that is showing an ellipse with the sun as one focus. Next law, the planets will cover equal distances in equal time, I think it was. That's probably not correct. But as far as I know, it shall travel faster the closer it gets to the sun, and slower the farther it gets. So let's see here. Alright, this is its distance from its orbital parent, which is the sun in this case. Now, as we see this distance go up, its speed decreases, but as the distance decreases, its speed increases. An inverse variation, if you will. Yes, so I believe that is the second law shown off. Now, next we shall do some calculations with Kepler's third law. The orbital period squared is equal to the distance cubed. Now we're going to want to put this into years, and I've already put it into astronomical units. So we shall do some simple calculations using the Steam web browser. Very glad I have this. We'll just say the average is between 300 and 470. 0.3, 0.47. So that's about 0.385-ish. Cubed. Now we should... Though this may not be a good example, I had issues with this before. Well, it's actually fairly close. Okay. Of course, I'm guessing the average distance here, but it is fairly close. I'm satisfied with that. Now, of course, I've only shown these with Mercury, so I should show these off with others. Venus, it's a bit harder to tell, but it does not have a perfect circle for an orbit, I don't think. Again, hard to tell. actually quite hard because I can't figure out where the sun is in relation to the center. For all I know, sun could be the center, but it's really hard to tell because of how far away it is. I guess I could zoom out some, but it still doesn't help any. Well, I'll leave it at that with Mercury. I'll leave Kepler's first law to Mercury, because it's, again, hard to tell. I'm done repeating myself now. Venus is traveling again to astronomical units. As its distance increases, well, its speed decreases. And as its distance is decreasing, its speed started increasing. I'm just assuming that the differences are so minuscule it's hard to tell, or it makes a very slow change. Now let us try the third law. Averages, let's see, lowest it's 713. Tops off at 723, so 0.78. And 0.615 squared. Again, it's fairly close. Of course it's not perfect, but I am merely guessing with astronomical units. Now, let us try, well, Earth would be pointless because it's always 1. Well, I guess we can show off the second law. Distance in astronomical units roughly averages 1. As its speed is, or distance is increasing, its speed is noticeably decreasing. But now its distance is going to start decreasing, speed increasing. Anyways, I shall not try the third law because that is the basis of the third law and therefore it would be pointless. Now, with Mars. It's more easily noticeable that the sun is not the center here. The focus, or secondary focus, is around here. Distance is, I presume, increasing, and speed is decreasing. And shortly, distance should start decreasing, and therefore speed should start increasing. I believe we are topping off, and it's coming back down. Yes, it is. So 1.66 is the top, and we're going to shortly find the bottom. Very slow process. 1.38. So averaging that should be I gotta think. Is that 28? Yes, 28. So 14, that's 52. 1.52 and 1.88 squared. Distance cubed is fairly close to times squared. Guessing is not going to let it be perfect, but it's fairly close. I am satisfied. I think I have shown off Kepler's laws in this. It is a fairly accurate game. The people who made this use real ignore that. The people who made this game tried to keep it as accurate as possible, so that way you could simulate a bunch of stuff. For example, you could... Well, let's do this over here. Actually, no. We're going to launch the sun into the sun. And supernova in a few seconds. 3, 2... Oh. Well, they just went supernova and everything's starting to freak out. They're all going straight out from the explosion. And for good measure, let us throw in a black hole. Because why not? Ooh, interesting. Black hole right here. Oh, seems to be glowing. Interesting. And it's gone. Where did... Oh, there's the black hole. Well, I've not had my fun yet. Let's chuck the Earth in. What else is there? Neptune. You thought you could get away? No. Oh. Superheated something. Mercury. Say goodbye. Oh, and it's gone. Let's slow this down. Now, it's around a day a second. As you can see, the fragments were just pulled back in, and I'm assuming added to the mass of Neptune. I guess for another test, we'll just... Let's see what happens. And it's all being sucked in. It's a pretty slow-moving fragment. And it's just gone. Now, if we were to put a sun next to it, let's see, let's put this still at right about there. And it just got sucked in. That's what happens when it goes supernova again. That was not my intention. Oh well, it is fine. Let's see how many suns this black hole can absorb. Quite a few. Oh, caused another supernova. That's a shame. Alright, let's send in Earth. And it went around to orbit a bit, and it still got sucked in. Let's give it a further orbit. Nope, it's still getting sucked in. Well, that's a shame. I can't even see what's happening. Alright. Now, oh, just a bunch of meteorites, asteroids, the whole 9 yards, as they say. And the fragments just orbiting it, as it should be. I think I've shown this off fairly well. Ooh, the supernova fragments here. Well, I can't do anything with it. And if I zoom out, it's basically a Big Bang. Let's spawn the Milky Way galaxy. We spawn the Milky Way. And it calls it a supermassive black hole. there's the dark matter. Ah, dark matter. Now let's throw in Sagittarius A. If I can find it. Ah, here we go. And then we'll just plop that in over there. Just placing this in everywhere, seeing what happens. And let's speed this up to years per second. Uh-oh, we're having issues with this, it would seem. Let's see what happens in 5 years. Having some issues here. This is a shame. I wanted to see what happens in 5 years. Well, it would seem that that's the end of what we're gonna get. Alright, I've had enough fooling around. Salutations, travelers. It's a greeting and a farewell. Onwards, Sayushima. I'm just going to put down the microphone.